This is Hydrology, a water balance approach, Chapter 2, Lecture 3. I'm Dr. Marty Matlock. We are using three sources for this information as our primary reference material: Forced Hydrology, Fundamentals of Hydrology, and Hydrology for Water Management from Chang, Davey, and Thompson, respectively. Incredibly good reference documents. I would encourage you to seek them out. If you need to build your library, these are three good places to start. As you recall, when we talked about watersheds, we started to put some relationships together in the dynamics of water movement through the watersheds in its various forms. So evaporation, transpiration, precipitation, infiltration, surface runoff, groundwater. These relationships are mathematically quantifiable. We call that process the water balance. So the thermodynamic laws that constrain phenomena at the atomic and larger levels in our universe also apply to watersheds. Energy is neither created nor destroyed. The same goes for mass. It's a compact form of energy. So water isn't created or destroyed. It just moves around. All systems move from a condition of higher to lower energy states. Entropy always wins, and water runs down an energy gradient. In watersheds, that's typically downhill, but if you apply energy like electricity and run a pump, you can move water uphill. And sometimes you can take kinetic energy. Water moving downhill very fast can hit a ramp and move uphill. We can make standing waves that way. It's a very cool thing to do in a river if you like to surf in kayaks. Simply put, in a hydrologic system, basin, watershed, drainage area, the law of conservation applies to water input must be equal to water output plus storage. So input equals output plus storage. Very simple. That's the water balance. We could stop right here, but that would be no fun. Let's give some definitions to these things. The components of the hydrologic budget: V equals water vapor in terms of mass. P sub T equals precipitation. So for the globe, on average, the amount of water in the atmosphere volatilizing into the atmosphere as water vapor equals the amount of precipitation on some time scheme like annually on average. So the average PT over land is about 746 millimeters per year. The average precipitation over the ocean is quite a bit larger than that, 1,066 millimeters per year. Since Earth's surface is almost 59% ocean, the ocean receives 3.5 times the rainfall as land. Most of the rain falls in the ocean. That's a fundamental truism, just like evaporation drives the hydrodynamic cycle. Of course, V, the mass of water vapor in the atmosphere, is greater than PT over the ocean, which is how water mass is transported over land. So they're not in equilibrium everywhere. Over the entire planet, over an annual cycle, they're roughly in equilibrium, but not instantaneously in a particular place. Thank goodness, that's how we get rain. A more explicit expression of the water balance at the global scale is the water vapor in the atmosphere equals precipitation plus runoff, where runoff is RO. Runoff is RO is runoff from the land. You can organize that as V equals precipitation plus runoff from the land, or V minus precipitation plus runoff from the land equals 0. Since overland precipitation is greater than evaporation, PT minus V, the vapor over the land, equals RO. That's why we have rivers and streams in areas where precipitation is greater than evaporation. There are some places on the planet where V, the amount of water vapor in the atmosphere, is greater than precipitation. You don't have runoff there. We call those deserts. This is for global scale balance. The annual precipitation over the entire continental United States, CONUS, on average is 76 centimeters, 760 millimeters per year. Recall that length, that's 760 millimeters, or 0.76 meters, times area, square meters, gives us volume, cubic meters. So this is fundamental unit conversion. L times LL gives you L3, LLL, which is the unit of volume. So that's how we come up with those cute little globes of water on planet Earth that we showed several lectures back. For the U.S., about 550 millimeters, a little over half a meter per year, is vaporized back into the atmosphere through evaporation, on average, on the planet, and evapotranspiration, E and ET respectively. Now, evaporation is just what you know, but evapotranspiration is the water that goes back to the atmosphere through living organisms, plants. Transpiration is the mechanism by which plants move water from the soil up through their leaves and evaporates. And that process is critical for plant life because that's the pump that moves nutrients into the plant tissues from the soil. So the remaining 210 millimeters per annum per year /A or AN typically means year, becomes runoff or infiltrates to the groundwater, INF. You can see on a global basis the annual water balance of Earth by different investigators, because these vary based upon assumptions you make. You roughly have precipitation between 745 millimeters and 800 millimeters a year, evaporation between 475 and 490 millimeters a year roughly, and runoff between 270 and 315 millimeters per year. Of course, these vary dramatically by where you are. And then, of course, in the ocean, these shift around significantly because of the amount of vapor evaporation from the ocean and rainfall to the ocean is significantly greater. And runoff to the ocean, I don't understand that one, but that's Chang describes that. I assume that the ocean runoff is near ocean land, edge of ocean land. So global PT equals V, globally precipitation equals volatilization. So that number is 973 on average according to Baumgartner. According to UNESCO, it's 1,130. So pick your poison, but it's roughly over 1,000, or a meter per year. So if we say that a meter per year is falling from the atmosphere and evaporating back to the atmosphere on a particular square meter of land every year, you get a pretty good sense of the volume of water movement on the land. And by the way, that square meter of land plus that meter of rainfall coming down gives you 1,000 liters of water, or a kilogram, or 1,000 kilograms of water, which is a metric ton of water every year. That's a heavy amount of water hitting the land and volatilizing back up every year. Now, the inflow of water into the continental United States is from the Pacific Ocean and Gulf of Mexico. The oceans give us our water, and it flows eastward and out. So IV inflow, and it flows eastward and out OV over the Atlantic Ocean. So IV inflow from the Gulf of Mexico and the Pacific plus vapor in the atmosphere minus precipitation equals what goes out. So for the continental United States, inflow from the oceans is about 1,220 millimeters per year, or 3.44 millimeters per day. Outflow is about 1,010 millimeters per year, or 2.77 millimeters per day. The difference, 0.7 millimeters per day, is what stays on the land. Not much. We know that rainfall is not uniformly distributed across the United States. Here we're looking at the TR55 rainfall charts, which you're going to become very familiar with next week as we talk about precipitation, shows the impact of mountain ranges. And you should be able to tell me what kind of storm flow or storm events those mountain ranges cause when we talk about these next week in a quiz or an exam. As the weather moves, as rainfall moves from the Gulf of Mexico up and then out to the Atlantic, it causes significant amount of precipitation through the eastern seaboard mountains, from the Alleghenies all the way down through the Appalachians. Sounds like a folk song. So, our water balance. Basin level water balances are different than global water balances. We have smaller time steps and geospatial steps, so we have more things to consider. We have higher disequilibrium for a given time step than the global water balance. So you have a lot more compartments where water can be stored. We talked about those in the previous lectures. Everything's connected, even these lectures. Therefore, we need to account for more partitions of water in the system. This applies across all scales, from Huck 2 to Huck 12, and even smaller for project sites, which one of your homework is covering. So we consider runoff out of a basin to be stream flow, represented as Q. So runoff accumulates and then leaves a basin in a channel typically. So that's Q. Basins store water in surface reservoirs, pools, ponds, wetlands, lakes, referred to as S. Change in storage, delta S, especially man-made reservoirs, impact Q dramatically. Think about our own reservoir, Beaver Lake. It stores water, so we have a lot of rainfall after a dry period, and water in the White River downstream of the Beaver Dam does not reflect that rainfall because change of storage is increasing. If we have a lot of flooding and the gates are open, or we're generating electricity, we're getting more water out in the White River than we're actually getting from rainfall. So that change in storage in some systems can dominate stream flow. You have to understand your streams to predict flows. Precipitation, which we've been calling PT, we'll just simplify to P from now on, drives water balance in these basins. So the standard water balance for a basin equals precipitation minus stream flow out, which is also runoff, minus evapotranspiration, which is ET plus transpiration, minus infiltration into the soil, minus change of storage equals 0. It all balances. Another way to look at this is to think about it in terms of what we really as hydrologists are concerned about, which is Q, flow in the rivers. We're managing and designing those. So to predict Q, we have to know P, we have to estimate ET, we have to know infiltration, and we have to understand delta S. And in many cases, the only thing we can control is delta S. So if we're going to control Q, we have to change delta S, change in storage. As we look at precipitation on the land, change of storage in the land, infiltration into the subsoil and into the groundwater, evapotranspiration everywhere, Q back to the ocean. Through flow or interflow is a really complicated phenomena. We'll dig into that a little bit, but it's really hard to predict because it's so location specific. However, it can be designed. I've actually designed several interflow systems for stream restoration that are quite fun. So let's move away from the cartoon and more to a conceptual systems diagram, remembering that we're talking about volumes, container volumes, and so that each have a certain capacity in the system. So precipitation, rainfall, is either intercepted by vegetation or hits the ground directly, and that leads to either overland flow and then hits the soil. That leads to infiltration and through flow, which leads to stream flow, groundwater storage, which leads to base flow, which leads to stream flow, Q, and that change of storage in the soil, above the soil, and to a lesser extent in groundwater. And then all of this also evaporates in the meantime. Stream flow goes to the ocean, and it's evaporating all the while. So evaporation is the entropic engine driving and pulling, pushing and pulling the hydrologic cycle and the water balance at all time. We'll spend a lot of time, at least a week, on ET, just so that you understand how to quantify it, how to measure it, understand its complexity. This basically defines the rest of our course: Q, P, ET, infiltration, change, and storage. These are the things we'll talk about in the remaining 4 weeks of this course. The water balance approach is very powerful. You can calculate a lot of important things with this work. I worked with the World Resources Institute over the last 10 years to develop and conceptualize a geospatial water balance modeling visualization tool called Aqueduct. Aqueduct you have links to in the webpage in both your notes as well as in Blackboard. Aqueduct is an incredibly powerful mapping system. We can assess water risk, food risks, country rankings, and floods with Aqueduct. Now, these are a high geospatial resolution, that is a fairly large resolution. You can zoom in a little bit, but it gets pixelated pretty quick. So it's really subcontinent level resolution, but it's incredibly powerful. So if we open Aqueduct for water risk, we can see that we have a menu on the left of types of water risk. So if we look at overall water risk, which is a cumulative of all of these, you can see that we have from low to extremely high water risk around the world. You can zoom in and out of this map. You can truncate this. This little blue arrow makes this menu go away, so you can set the image and copy the image into a document. So this is in WRI.org Applications Aqueduct Water Risk Atlas. We can look at these annually or monthly for temporal resolutions. You can collapse this menu as well, so you have full control in the visualization. It's incredibly visually powerful. I've worked with Mars Corporation, Tyson Foods, Cargill, and others to get them to use Aqueduct, and they now support it, to get them to use this for their own water risk management in their corporations. By the way, look at the patterns here, the geospatial patterns. You should start recognizing those as Huck 8s. Physical scarcity or physical risk of scarcity from water budget models really is what water risk means. So we have a number of types of water risk. Water stress, which really is the amount of water available over the water needed. Water depletion, which is the change of water available over water needed. Interannual variability, the change over each year. Seasonal variability, the change over the 4 seasons of the year. Groundwater table declines, riverine flood risk, coastal flood risk, drought risks. All of these you can analyze individually. You can look at physical risk quality for untreated connected wastewater, coastal eutrophication potential, and regulatory and reputational risk from unimproved or no drinking water, unimproved no sanitation, peak risk, regulatory reputational risk from ESG risk index. Just a number of the powerful tools that you can develop using this simple water balance strategy when you have the data. Data are powerful things. So if we look at drought risk, annual drought risk, for example, we can see that right now annual drought risk across the central United States, where we grow most of our crops, is medium. It's low to low medium across most of the rest of the U.S. Now, that's pretty accurate. The fact is we've had about every decade significant droughts, and that's what you could think of as the medium. It really represents a drought every decade. Medium high represents a drought every 5 years, and high represents a drought every 3rd year. Now, if you're in Russia, you got problems. If you're in India, you got problems. If you're in China, where they grow all their crops, in this region, you've got problems. Water availability is a major, major concern for global stability in the coming decades. And this is one of the reasons why. Riverine flood risk is fascinating that we can actually calculate this with a mass balance model based upon, again, annual or monthly changes. Of course, we have seasonal flooding in some areas. That's just the nature of the ecosystem across the tropics, and that's pretty cool. But where this really gets important is if you look at their flood mapping with cities, then it becomes even more informative. So let's talk about future scenarios. Future scenarios go from 2030, which is a decade from now, to 2040, and they're using 3 climate change scenarios. A pessimistic one, which means we just keep burning up coal in the atmosphere. A business as usual, which means we increase. Business as usual, which means we stop it at the current level. And optimistic, which means we actually reduce greenhouse gas emissions and therefore climate change. So those are 3 low, medium, high climate change scenarios. Actually, high, medium, low climate change scenarios. And we can look at things at 4 indicators: water stress, seasonal variability, water supply, and water demand from an absolute perspective or change in baseline perspective. Change in baseline means that it's looking at 2030 from 2020 or 2019 when the most recent data sets are. That's really the most informative way to view this. So if I look at an absolute value of water supply using a pessimistic 2040 estimator, looking at water supply, the lighter colors have less water, less than a centimeter supply per unit area. The dark blue have a lot of water. Mississippi River, lots of water. The Amazon, lots of water. The Nile, you can see our rivers here. Nile, the Congo, lots of water. But the challenge is there are many places in the world that are not going to have a lot of water in the coming decades. And that water scarcity is going to drive a lot of conflict, as we've said earlier. If we look at change from baseline, from water demand, this is where we start looking at population demands. So where the dark red is 1.7 times or greater increases you can start seeing that we're going to have incredible increases in water demand as humanity grows from 7.35 billion to 10 billion. Oh, well, in 2040 will only be about 8.5 billion. So add another billion people on the planet in the next 20 years. And then those folks are going to be more prosperous, and more prosperity means more water demand. So the good news is that people will be more prosperous and there'll be more of us. The bad news is we need more water, and it's going to cause stress. So this is a way to visualize that stress and understand it. So I provided some other further reading for you, and the link to the to Aqueduct is on your homework assignment on Blackboard, as well as directly linked to Blackboard Week 1. Please save that link because you're going to use it extensively through this class. Take a look at the NOAA rainfall frequency and climate maps and their global precipitation measurements from NASA, as well as USGS streamflow monitoring site. Go ahead and take a look at those because we're going to use those starting next week. This concludes Week 1 lectures for hydrology. Thank you for your attention.